Hello, I'm Llewellyn Falco, and I'm Agile Technical Coach, but I mean to record a video about test-driven math for many years now, and I just never was able to get it quite perfect. And so I wanted to get this video out just to explain what the concept is. Hopefully there'll be more videos in the future that sort of delve into this, but I wanted to show how I can take some of the lessons from property-based testing and apply it in a completely different domain of mathematics. So let's do some math. Here we are at Desmos, and let's just do some calculus. So here I have a function, and let's do something interesting. So okay, so that's a nice little graph, and now I want to create the derivative of that. I don't know. It's like that. Maybe that's the derivative. Maybe it's not. I mean, who knows? And if we look at traditional mathematics, the way we would do this is we'd open up the book and we'd look in the back. That's sort of analysis to like our unit testing. Or we might just check our work. That would be sort of analysis to a code review. But we've learned that there's this other thing called property-based testing. So let's take a look at that. And to do that, we really need to think about what that derivative means. And so let's take a point on this thing. So we'll take 1 and then whatever f of 1 is. So now we've got that point. And what this derivative means is that should be the slope of the line at that point. So we know what point slope line is. So this is a point slope line is y minus or y1 minus y1 times the slope times x1 minus x. And we know what x1 is. That was 1. And we know what y1 was because that's up here. That's f of 1. And we know what m is. M is our derivative. So that's going to be d of 1. And let's turn that off so we don't get confused. And we can clearly see here that this is not the slope of the tangent. This is not going right next to the line. So let's see if we can fix up this derivative. It should be -6. Oh, still not looking very good. Square that. 5. This should be 10x. Yeah, okay, that's looking pretty good. Now this is the slope at the tangent to this line here. I mean, it works for 1. What about if we try 2 here? So switch all those 1s to 2s. Yeah, could be it. Let's get a little more generic. Let's just try saying A. So I'm going to swap all my 2s for A. And then let's add a little slider for A. Now I can sort of see it. Yeah, no, that definitely looks like it's working. Sort of going here between like 1 and 2. So let's just start at -1 and go to 2 and hit a play button there. And yeah, now it's not proof, but it's pretty strong evidence that we've gotten our derivative correct. And this doesn't really depend on what the formula was. So let's say we had just a cosine of x. All right, well, we can clearly see it's wrong here. Cosines and sines usually go together, so let's try sine x. Oh no, that's definitely wrong. Let's try negative sine x. And let's take a look at that from, say, -2 to, let's go all the way to 4 here. Yeah, so because I'm exposing the property, I can check if I have the right answer, even if I don't know what the right answer is. I don't need to know that this is the right answer to tell you it is the right answer or it isn't the right answer. Which means once you do this, you should never get a math problem wrong again by accident. And an interesting thing is the property of this actually helps to understand the math as opposed to, like, cheating or checking to just make sure you got the right answer. right? Because now you're actually getting a better understanding of why this might be the answer and how that answer relates to it mathematically. And I've been able to come up with properties for almost every part of mathematics with a very notable exception of statistics. I'm not sure how to apply this here. But so let's take a look at just one other case. In this case, we're going to look at the inverse. So let's do 3x cubed. And now we want some inverse of that. And I don't know, I guess that's like maybe a third x. And so you can do this again with the graph, right? But you can also spot check this. So let's do f of, or I, both ways work, I of f of, now you could do a number like 2, but that's not going to be that helpful. So let's do something like a little more interesting, 2.1452. And if I've done it right, I should get that number right back, which I am not getting back. So let's do this again, and let's take 1/3 of x and take that entire thing to the cube root. And now you can see I put 2.154. This is a little bit hard to check, so let's do 2.12345, and 2.12345 comes right back. So an easy way to spot check that I got everything correct. So that's test-driven math using property-based testing. There's a whole world of ways you can do this depending on what kind of problem you're trying to check. This is a technique I created about 5 years back now when a friend was going through Khan Academy. And Khan Academy has this great thing where they go for expertise. So you have to get 5 questions right in a row before you can move on. And I really like that, but it can be a little bit frustrating when you're doing like differential calculus and all of a sudden you've spent 15, 20 minutes on each problem and you mess up one little calculation and you have to do like another 2 hours worth of work again. And so we were looking for ways, how can we check our work? And that's where we came up with this idea of maybe we can apply some of the techniques from property-based testing to mathematics. So try it out. I hope you like it. I encourage you to play with testing in general, but also to take some things that you might have discovered in software and computing and take them to other domains, because there's an amazing amount of things that transfer over in really neat and powerful ways. I'm Llewellyn Falco, and happy testing.